Thank you all very much for joining us today for this event jointly organized by the medical section of the Royal Statistical Society and also the Oxford local group of the Royal Statistical Society. We're very fortunate to have with us today Professor Rhian Daniel and Professor Daniel Farewell, who are going to speak about regression by composition. So, please.
Thank you very much. Thank you, Christiana. Thank you for the invitation. And sorry for the slight delay because of the technical difficulties, but hopefully everyone can see the slides online as well as here and can hear me clearly enough. Thank you very much. So we are both going to talk about regression by composition in a way, but you have to wait until Daniel's talk to have the proper definition of regression by composition. And my talk is going to be a little bit introductory, really describing the path that we took to thinking about this rather large class of models that we are calling regression by composition. It's joint work with Anders Whitford and Matt Stenstrud. And as I speak, I will, especially in terms of Anders' contributions, I will be mentioning him very frequently. So Anders is a medical doctor who's been trained in epidemiology, working now in Norway. He's Norwegian but has worked in other places as well. And we've really enjoyed this collaboration with him because he's a medical doctor with an incredible intuition for statistics, it seems to us. So in a way, all the ingredients in regression by composition were suggested to us by Anders in a document that he wrote quite a few years ago now. And he felt he needed some statistical input and so asked us to get involved. And little did we know at the time that it would become such an enjoyable and interesting project. So in my in my first talk now, I'm going to talk about regression models that we know, so GLMs, and a particular way of thinking about them. And then, how do I advance? Yeah, okay, that will work. Never mind. So I'll talk about generalized linear models and something called Lambda plots, if you're not familiar with them. And then, just checking there was no message online that and then I will talk a bit about mechanistic causal models, a way of thinking about specifically by binary outcome regression. Noise we should be concerned about. I think there would I carry on. And yes, well, you see what I mean when I get to it. So, okay. Generalized linear models, and specifically in medical studies. So in medical studies, and quite likely beyond as well, but certainly in the applications we tend to work with, I think you'll agree that one predictor variable is often privileged. So the treatment or the exposure in the regression model is special in some way, whereas the other predictors or the other covariates are included there, so for example, to increase precision about the estimated treatment effect, or in an observational study to control for confounding and other reasons as well. And so we sort of think, at least in my talk, we will be thinking from this point of view. So we'll write Y for the outcome, X for the treatment or the exposure, and then a vector C for the covariates. And so a generalized linear model, of course, specifies the form of the conditional outcome mean via some link function of G. So, of course, it doesn't have to be of this sort of this simpler form. We could have product terms between the various covariates here. I don't really mind. I'm just putting that as one lump of a term, including C. There could also be product terms between X and C, which I've chosen to omit here, but we'll come back to that. And so, for example, if we think of a binary Y, then of course this conditional expectation is the conditional probability of Y equals 1. And if X2 is binary, then this GLM implies this relationship between the, if you like, the untreated conditional risk and the treated conditional risk as defined here. So in other words, to get from the untreated conditional risk to the treated conditional risk in a GLM, you first apply the link function, then you add some number on the scale of the link function, and then you transform back to the probability scale via G minus 1. And the nature of this transformation from P0 to P1 implies by G and beta can be nicely visualized in Labick plots. So maybe I should say, in general, of course, the beta could depend on C if we did have product terms in the model here. But in the simple case where it doesn't, then this is just a single number. And so a Labick plot is simply a plot of P1 of C against P0 of C. So we see some examples here. On the left-hand side, I've put the Labick plot for logistic regression. Then for a GLM with a log link, GLM with a complementary log link, and then a GLM with an identity link. Of course, there are many, many others for GLMs with all sorts of other link functions. And we see that G, the link function, determines the shape of this relationship, whereas beta refers to reflects the size of the transformation, if you like. So they all include an identity, the dashed grey line straight line in the middle on the 45-degree angle, where P0 of C is equal to 1 of C, and then the red lines or curves above are for harmful exposure effects that make the outcome, the bad outcome, if we've coded it that way, more likely under exposure. And the green lines are where the bad outcome is less likely under treatments and not. And it's sort of pretty nice, we feel, to look at GLMs this way, because many model features are illuminated. So, for example, the fact that some link functions lead to non-closed models, in the sense that some inputs, if you think of these as the input risks and the output risks, then of course, as we know, for a model that assumes a constant risk ratio, or a model with a log link, then there are some probabilities here which for a given beta would be transformed to something above 1, so not a probability. And likewise for the complementary log link, so a model that assumes a constant survival probability ratio, then there are small input risks that would be transformed to risks less than 0. And then for the linear probability model, of course, there are problems at either end, but for logistic regression, the probabilities are transformed by probability. It's one of the reasons that people like logistic regression. Another thing that is illuminated quite nicely is non-collapsibility. So the idea that even in a randomized study, if you have a baseline covariate that is predictive of the outcome, then you will estimate a different odds ratio for treatment if you include or don't include that covariate. Or I see now that I think yes, it's when people are arriving at the Teams call that we get that, but I guess someone else is admitting that. So, for example, what I've plotted here is the input risk for 4 different values, 0.1, 0.2, 0.3, 0.4, I think, and where those get transformed to if the beta is the one that corresponds to this in the logistic regression. And what we have, the cross here, the X here, I mean, is where it is the average of those 4, whereas the cross, the plus, is where the average of the 4 gets transformed. So let me say that again. The plus is where the average of the input risks gets transformed to under that beta and that logistic regression. whereas the x is the average of the transformed risks. And we see that the average of the transformed risks is closer to the null than the transformation of the average risks. So this is simply Jensen's inequality at play, that if you, for a non-linear transformation, if you average and then transform, it's not the same as if you transform and then average. Whereas for the other linear functions I've chosen to show here, for the other models I've chosen to show here, that phenomenon does not occur because they are straight lines. We also see that there are some fixed points. So logistic regression has two fixed points. If you cannot have the event when untreated, you also cannot have the event when treated. And also if the event is inevitable under no treatment, it's also inevitable under treatment. Whereas GLM with a log link has one fixed point here, GLM with a complementary log link has one fixed point here, and the GLM with the identity link has no fixed point. We'll come back to the idea of fixed points later. I think it also illustrates nicely another thing that is often talked about, which is that effect modification is a scale-dependent concept. In other words, if I choose 2 points that lie on the same curve here, so for these 2 input risks, the same constant odds ratio applies, then they lie on different lines for the other models. But there's nothing special about this. If I chose dots on the same line here, they would be on different lines and curves everywhere else. So the lack of effect modification, except under the null, of course, if the 2 points were on the identity line, then they would be on the identity line everywhere. But away from the null, effect modification or lack of effect modification on one scale implies effect modification on any other scale. I think these plots also illustrate extrapolation very well. So here is an example taken from a Nature paper where the outcome was, so it was an RCT comparing oral symbiotics versus placebo for the development of sepsis in newborn babies in rural India. There were 5 baseline covariates, and if you fit a logistic regression to those data, or a GLM with a log link, the input risks, of course, are slightly different for this final transformation of treatment from the 2 models, because in one model everything is modeled by the log link, and in the other everything is modeled by the logic link. So the input probabilities vary a bit, and then the transformed probabilities vary a bit, but we see that they are extremely close and almost indistinguishable. So the X's here are the logistic regression points, and the pluses are the log link GLM. And yet, if you zoom out to see what the consequences are at higher risks, higher baseline risks of believing this effect measure either expressed as a risk ratio or as an odds ratio, you would relate to very different transformed risks appear. Right? I think this is a real problem in practice. The extent to which it's a problem depends on the setting, of course. But if we think that most RCTs are conducted in highly selected populations, then when the results of those RCTs are used in practice, doctors are perhaps only informally, but they probably are performing these kinds of extrapolations in order to decide whether a particular treatment is a good idea for a patient in front of them who might have a baseline, an untreated risk that's quite different from the risks of the people in the trial. Okay, so the second half of my talk then is going to be on sort of mechanistic fundamental causal models and how they may help us sometimes to choose between different choices of models or binary outcomes. So we see that the model choice matters and that the data aren't always informative. So that would be the case in this. I don't know how to go back. Oh no, this is working. Okay. In this example, the data would be useless in informing us whether a logic link or a log link or indeed any other link is the right one to choose. If the consequences for the choice tree are substantial or fully. So, and this was Anders' starting point in thinking about this problem. He was aware of the heated debates in the literature, the long-standing debates about whether things should be reported as odds ratios or risk ratios, and wanted to bring a more fundamental approach to thinking about, is there some way of reasoning which is the correct model in the absence of other ways of treating. So the idea is based on the Ken Rothman causal pies paper from 1976. In other words, that any outcome, and here we are still thinking of the binary outcome, any binary outcome y is determined by x and other unmeasured things. So if you're familiar with these pies, there are ways of expressing that. So please forgive my abuse of notation here. Until now, I've been talking about x as if it's a binary random variable. I will now use the letter x to mean the event that x is equal to 1. So that not x is the event that x is equal to 0. It makes this slightly easier to read, I think, and hopefully it's not confusing. I'll go back to them being random variables. But this is the event of experiencing the outcome is the union of these events, u, x and a, not x and b. In other words, this is saying that there are 3 ways in which the event can happen, either because u happens, or because you are treated and a happens, or you are untreated and b happens. We'll see an example in a moment. So those are causal pies for y. And then you can also have causal pies for not y, for avoiding y, if you like. So the event y does not happen when, again, either w happens, or you are treated and d happens, or you are not treated and e happens. Or indeed, of course, more than one of these things can occur together. So I think it's easier to understand with an example. So the first example from Anders' work has, I think, a population of children with suspected strep throat and an RCT comparing penicillin versus placebo. And then the outcome is whether or not they develop rheumatic fever within some period after initiation of treatment. And so the idea here is that, well, so first of all, sometimes it's more natural to think of causal pies for avoiding the outcome than for experiencing the outcome. This is a slightly second point. We'll come back to this in a moment. But if for this example, it feels natural to think of causal pies for not y. So in other words, rheumatic fever will be avoided either if the body's own immune system would clear the infection on its own, so you don't really need any treatment, it would do so whether you are treated or not, or you are treated and essentially the treatment works for you. Here I've expressed it as, you should take the assigned medication, so it's not going to work if you chuck it in the bin, whether it's penicillin or placebo. It will work if you are someone who, in addition, can metabolize penicillin in the normal way, and if the strain of infection that you have is susceptible to penicillin. So I know this is long-winded, but we can think of this always as penicillin works for you. Things align so that penicillin works for you. So in this example, there isn't even any E. There's no causal pie with not X in it. So that means that taking penicillin will help some people. It will help the people with the. It will be, in effect, it will be neutral for someone who who has W, because they would be fine anyway. But it doesn't harm anyone. There is no one who would only get dramatic fever because they took penicillin. And then there's the question, so these are back to being variables, if you like, now. So X, D, and W together determine Y in a way that I'll written down here. So you will avoid Y if you have W or both X and D. And so that's why they get these special red forward arrows to show that if you know X, D, and W, you will know Y for sure. And then I think the strong assumption, well, it could be argued that it's a strong assumption that the world operates in this way, of course. But if you're happy to take that rather large step, then there is also the assumption, which is, again, major, that the covariates affect W, but nothing else. So if you like, the elephant in the room is, well, why doesn't C also have an effect on D? Or why isn't there something else that renders D and W correlated? And we'll come back to that. But if we're prepared to think that the world is as simple as this, there are things. So the causal pi tells that not Y is equal to W union X and D, which means that Y is equal to not W in reflection, not X union not D. And that is helpful because then we can write the probability of Y equals 1, given treated as just the probability that W and D are 0. So, that is what we have here. So if X is 1, then this certainly will not happen. And therefore, for this to happen, we need both these to happen. And then the independence assumptions that we've drawn here allow us to simplify this to simply the property of W equals 0 given the covariates times the property of D equals 0. Of course, it wouldn't be this simple if we did have the correlation between these or that C was also affecting. And then the probability of Y equals 1 when untreated is simply a similar argument. So then this does happen. So it doesn't matter whether this happens or not. And so it's simply the probability of down in equals 0. And you see that if you divide this by this, you simply get the probability of D equals 0. So that's a constant risk ratio equal to the probability of penicillin not working for you. And therefore a GLM with a log link would be implied. And then we could play a same game with a different set. So this is the same setting, except that the outcome is now different. So the outcome now is whether or not you have anaphylactic shock on the day of treatment initiation. I'll go through this a little more quickly, but it turns out that a causal pi model of the other type is more natural here to argue for. And really that's saying that Y is equal to U union X and A, or not Y is equal to not U intersection and not X and not A. So this is now, A is that you have a severe allergy to penicillin. So that's going to mean that X works for you. Of course, working now is a bad thing. X will cause the anaphylaxis for you. And then the only way you can have anaphylactic shock on that day for a different reason is if you happen to be so unlucky that you have a severe reaction to something else on that same day. So that probably is quite unlikely, and yet the possibility of U has to exist. So under this model and these assumptions, we then have that the probability of Y equals 1 under treatment given C is 1 minus the probability of U equals 0 given C has the probability of A equals 0. Whereas the untreated risk is just 1 minus the probability of U, don't indeed the probability of U equals 1. And so that means that if you take the complement of these two probabilities and divide them with each other, you get the probability rate equals naught. So that leads to a constant survival probability ratio model, or a GNM with a complementary logging. So as I say, the elephant in the room is what if these A's and U's are not independent, and I'll come on to that a little later. But do you follow the logic, at least under these very simplified assumptions and simplified settings, that by thinking about how variation in the effect of X on Y comes about, if you like, why does X cause the outcome for some people and not others? Thinking it through in this way leads you to different models in different settings. So let's see if we can explore something a little bit more complicated. So the first two examples, both from Anders, were both under a monotonicity assumption. So the action of X was either neutral or harmful for everyone in example 2. And in the first example, it was either neutral or protective for everyone. So that's what we mean by monotone. But I will now consider an example where, at least to some small extent, we can expect non-monotonicity. We can expect X to help some people and harm others. And I don't think this is rare as a setting. I think there are many examples of exposures that maybe help the majority but harm some. And so I've tried to think of an example here. So let Y be hospitalization due to severe COVID-19 infection. X, the exposure, is vaccination. And then we have 3 other variables to consider, these sort of latent things that we don't know usually. One that's going to be relevant for the problem. So one is that normal immune response to the vaccine takes place. So of course we know that some people don't respond to the vaccine for whatever reason. So A will be that normal immune response to the vaccine takes place. Now, B is going to be that behavior substantially becomes riskier if knowingly vaccinated. So if you think back to 2021 when we all received our first vaccines, there were stories of some people, as soon as they received the vaccine, they stopped wearing masks, they mixed with other people much more. And this is, I think, what is perhaps a bit similar in many examples. There are many examples where, if you know you're using a low energy light bulb, you'll also be more likely to leave the light on. So this sort of thing that I think happens quite a lot in many, many different examples. And then U is going to be that you would be hospitalized if unvaccinated. So, U is that you are vulnerable, if you like. If you don't have U, that's another way of saying, so that the healthy ones are the ones with not U. So for them, vaccination doesn't really matter because it could matter if they have anyway, you'll see what I mean in a minute. So I think in this setting, it does get a little bit more complicated and more difficult to say it in words. But what I've got here is, so if you're unvaccinated, then you will be hospitalized if you have U. This is exactly the definition of U. You will have the outcome if unvaccinated. So if unvaccinated, U is Y. Whereas if you are vaccinated, then you will be hospitalized if both of these things happen. So first of all, the vaccine needs not to work for you. Otherwise, it doesn't matter what you do, you would be fine. But if the vaccine doesn't work for you, and either you would be hospitalized if unvaccinated, or the fact of being vaccinated makes you behave so much differently that you then are vulnerable, then you would be hospitalized. I think that's the way to think. And no doubt this is simplistic, because you could say there are many more factors at play, you could imagine making more elaborate versions of this as well. And at least it's a plausible setting in which we do have this non-monotonicity. And then if we again make the independence assertions that I think it actually doesn't matter if A and B are independent, which I could have included here, equation along B equals naught, and that wouldn't have changed anything. So it doesn't really matter if A and B are independent, but it does matter. Yes, I also intended to drop the conditional on C there, which is an assumption I am making at the moment, that C does not affect A and B. So sorry, that's a typo. But if you work through what this means when X is 1 and when X is 0, you end up with this probability for the treated risk and this for the untreated risk. And so you see what's happening is, and as I say, it shouldn't have a condition on C. It shouldn't have a condition on C, although this one could have a condition on B equals naught. That would not be a problem. So you see what we have here is we take the untreated risk, we take the complement of it, which is just this probability of U equals naught, multiply that by something, a constant, well, this shouldn't be there, and then take the complement of that. So that's like a survival ratio model. But then we multiply that by this constant. So that's more like a risk ratio model. So this is a composition of both of the previous transformations. And the Labi plot for that, so the Labi plot for first applying a risk ratio transformation and then a survival ratio transformation, or the other way around, the Labi plot turns out to be all of the increasing straight lines, including ones that cross the identity line, that cross that 45-degree angle dashed gray line. And that's the non-monotonicity coming in, because if it crosses the identity line, then clearly for people on one side of that crossing, the exposure is harmful, but for the ones on the other side, the exposure is protective. And yes, so here actually it looks a bit strange because what I've drawn are the composition of the ones I chose, the risk ratios I chose here and the survival ratios that I chose here. And that ends up giving us this sort of pattern, which is very like the sort of things used to stitch in primary school. They are all straight lines, but they sort of create this funny appearance of a curve. But really any increasing straight line is possible under the composition of some survival ratio with some risk ratio.
Yes, Clint, go back for one bit. The probability A equals 0 and the condition C. A is not correlated with C.
Yes, exactly. So this is a typo. There should be no hidden C there. Yes. So both under this simple model, at least, this is a constant, as is this. So it's, sorry about that. Exactly right. I didn't intend to have the conditional on C here. What I said you could have, I've also, in the picture, I've assumed that A and B are independent. That actually doesn't matter. So you could have here conditional on B equals naught, and this would still be just a constant. So it would still belong in this model class, if you like.
How do you estimate that?
So this will be Daniel's talk. So this is an example of a very simple regression by composition model that is not a GLM. So there's no link function G that will give you this Labe plot. It's a two-parameter transformation that is it's a composition of two transformations. It's a composition of first this type of transformation and then this one. So in a way, how one sets about estimating such a thing was exactly the problem that Anders came to us with in the beginning. So yes, you will hear more about estimation in Anders' talk. So in fact, what Anders was thinking was he he didn't in fact think of this composition model. He was in, so what I haven't told you is that in Anders's paper, this one, he has an argument for why in by no means all settings, but in a subset of biological settings, one can argue that if X lowers the risk of a bad outcome, this is the plausible model. So models for the pi models for not Y are more plausible in the sense that they will lead to more plausibly independent W's and D's. Whereas if the exposure is harmful, like in our anaphylaxis example, this kind of model is going to be more plausible, as in you will be more plausibly able to come up with a simple causal pi model for Y that satisfies independence of U and A. And therefore, he favors this switch relative risk model, which is a model, it's a hybrid model that chooses a portion of so if the exposure is protective, it chooses this model. And if it is harmful, it chooses this model. You get this sort of Venetian blind looking, or broken Venetian blind looking plot. That is nice because you see it's closed. Because do you remember that it's only the top half of this plot that is problematic for mapping probabilities to probabilities, and it's the bottom half of this plot. So if you take the bottom half of this and the top half of this, you end up with something that is collapsible and closed. So it has very appealing properties and has been talked about, for example, in this paper by Van der Laan and others in 2007, but also has origins far earlier in work by Mindel Sheps in 1958 and things, where she talks about counting the living or the dead, and it's about how you should choose between those, how you should choose between essentially the risk ratio and the survival probability ratio. But it's interesting that this composition model includes this. So because this is all increasing straight lines, it certainly includes all of the ones that are in the switch relative risk. It also includes more because it includes these non-monotone settings. Now, finally, I want to say a little bit about relaxing those independence assumptions. So, because this is important. So what happens if there is a reason why D and W are not independent? So they are correlated here. And so I've gone back to example 1, where this is rheumatic fever. And so far I've changed nothing. But now, when we would use this expression to work out the treated and untreated risks, we wouldn't get such a simple expression because we would have this conditional on F equals this less here. So I think you can see instinctively if you divide these one by the other, you will only get a constant if indeed this does not depend on F, which is the situation we already looked at. So when when there is no F, D and W are independent, then this is just a constant and it comes outside, and then you divide the same thing, not the same thing. You end up again with the property of D equals naught, which is obviously what we should obtain. But when this does depend non-trivially on F, some other possibly unknown variable that renders D and W correlated, then this divided by this will not be a constant risk ratio. And in fact, we can draw, so for a simple binary F, what I've drawn here is for a range of, so I've chosen one probability of D equals naught marginal, which is this point here, because do you see these, if you think of the fixed points here, so if the untreated risk is 0, it must mean that all of these are 0, which means that this also will be 0. And if this is 1, then all of these must be 1, and then this becomes just the probability of D equals naught, because you can add the C in there, because D and C are conditionally independent given F in this setting. So this if you trace that back to the y-axis, that 0.5 is the probability of d equals 0 marginally. But the Labe plots for P1 against P0 for non-trivial. So in the middle, I think I have the straight line where D does not depend on F. But then for increasingly positive associations between D and W due to F, and then for increasingly negative associations between W and D due to S, I've drawn what we say here. Of course, if F were measured, you could just condition on it. You could stratify on F. And of course, you do have one straight line for F equals 1 and a different straight line for F equals 0. And this is what I was showing. So I've just chosen one of these now. I think the bottom but one. And that's what you get when you just average these two, because the F equals 1 tend to have higher risks and the F equals 0 group tend to have lower risks. That's why the D and the W are correlated. And therefore, or if you like, that's why F and W are correlated. And so when you average, you're tending to pick this line for the higher risk and this line for the lower risk. So you end up with this. That's what this curve is made out of. But what's interesting, I think, and a good question to ask is, well, can these kinds of models ever lead you to logistic regression? And they could, but only if C is empty. So in other words, we're going to condition on F and C, but all of the C's and F's are in fact F's. So if all of the covariates affect both D and W, so all the covariates are here and there are none that only affect W. If that is the case, it's like saying you've got, a different straight line for each particular value of S and C, because there's no C except for F. So for every combination of covariate values, you have a different risk ratio that applies only for that particular level. And then you could imagine that if the stars align correctly, those would create a pattern that is exactly logistic regression. And indeed, that's the relationship between the D given S and the W given S probabilities that you would need to recover an odd proportional odds ratio, proportional odds model for different odds ratios. And you could do the same for the risk increasing half of the model as well. So how can we make statistical inference about the parameters of the Swedish relative risk was the question that Anders first came to us with. And so that's certainly something that, as you were asking, how on earth do we estimate these things and make inferences about them? But also another question that I suppose came more from Daniel was, does this idea of building flexible parametric models by composing transformations, not just for two different transformations for the same covariate, but also different transformations for different covariates, does this generalize beyond just binary stems and the sort of simple setting we talked about here? And the answer is yes. And so this is, I think, what Daniel will discuss in his talk. So thank you very much. That concludes my part, but I suppose we could take questions now if there are any on this before we move on.
What any questions from the people or with straight online and things like to either raising the child and youth and very kind for us.
Got a question regarding one of the DAGs. So one of the assumptions is you do is your covariates can only affect the outcome through the W or one of the pathways. What if there is a direct pathways from the covariates to outcome?
Yes, well, I suppose in this setup that is prohibited. by the fact that X, D, and W determine Y. So it doesn't leave any room for C to have an effect on Y other than through those. So this, yes, and I find it quite hard to reason whether, so of course any particular causal pi model, certainly the independence assumptions that if you're making those are clearly strong assumptions. The choice, if you're actually trying to specify what the pi's are, then of course any of those is something that you may dispute, and quite rightly so. For example, are there any pi's with not X in them? If I'm saying, let's suppose there are none, that's clearly an assumption that may not be valid. But what I'm not quite sure about is, so when you read the literature on these sufficient component cause models, he'll always say, let us assume that such a thing exists. And I'm not quite sure how big an assumption is that. I'm sure there would be people who'd be very uncomfortable assuming that you're almost assuming something very deterministic, but about things that you don't know. So it's clearly ridiculous to say that we can determine Y in any way, but to say that given these unmeasured, nebulous, large collection of things, Y could in principle be determined. I'm not sure how big an assumption. I think I'm comfortable making that assumption, but I'm also aware that I'm sure many people wouldn't, and I've not thought enough about what exactly is required to make such an assumption, I suppose, philosophically. But I think if you're prepared to assume that a causal pi model exists, then you are going to be prepared to assume that these things determine Y. And then I think it's reasonable to say that the role of C is to affect or to be correlated with. I didn't say that, but I don't think at any point did we use the fact that C is a cause of W. C could share unmeasured common causes with W, and everything I said would be fine. And then, of course, there's the assumption for the constant log risk ratio model and for the constant log survival probability model that C affects Y only via W and not also via D. And of course, that is it. I didn't say anything much about X. Of course, in a randomized study, it's sensible that X sort of lives on its own up there. Of course, if it was an observational study, then that would not be the case. Yes. And one that worries me also.
And other questions you have that? Only in the one online. Well, these spot many we can read that us or there will be opportunities.
It's any talks on later. Emma. Yeah, that's the yes person. There's no titles on it. So, just before I jump into my part of the talk, I just because I'm really interested in the question you've raised, it was something actually Rhian and I were talking about just yesterday. I don't know to what extent this is interesting, but the sort of measure theoretic formulation of random variables. A random variable is precisely a deterministic function from the sample space to somehow the range of the random variable. You know, we write y
is a function from omega to the range of y, the real numbers or whatever. And by no means do you have to interpret it this way, but one possible interpretation of that is, in some sense, the omega, the sample space, is like the initial conditions of the relevant universe. All the sort of upstream stuff in Rhian's DAGs, and the rest is deterministic. So that's just to sort of build on the general interest of this. One of the reasons this has been, Anders's way of thinking has been really challenging to us, is because I think until we talked and met with him, we basically thought of statistical models as being quite empirical constructions. We just allow the data to guide where, what the model should look like. That's a good fit, that's not a good fit. But as Rhian's described really clearly, this idea that, okay, that's all very well within the range of the data, but if, as we often want to do, to take it outside that range, we're going to need something more than that to guide us. And so this idea of deriving the functional form of the model from first principles, we found that a really interesting idea, quite challenging, sort of quite a new way of thinking about things. And the fact that, okay, maybe it's a simple setup, but that from a simple setup, you can derive a recognizable model and say, under some assumptions, this is the model we should be fitting. So it really speaks into this important question about transporting effects or generalizing effects. And I don't think there's any reason that kind of logic needs to be restricted to binary models as well. So just sort of throwing that out there as something that we both, but would also encourage anybody to think more about, because I think it's a challenging idea. Before I tell you, as Rhian's promised, I'm going to try and build up how we think about this class of models, and it does indeed lead to a way of fitting models that are not GLMs and so on. I just wanted to sort of say briefly what a thrill it is to be here. It's a real honor to talk here in Oxford, as always. I did my undergraduate here, but it's the first talk I've ever given. We were reflecting on the way up here of the way you don't often appreciate what you have when you have it. So what a wonderful city to work in, what a wonderful city to do research in. But I'm really appreciative of you all being here, giving up. I mean, how often do you get 1 hour, let alone 2 hours to talk to people about a topic? So thank you very much for being here. I'm very happy to be interrupted as we go along. In fact, I generally tend to like that because it means at least one person is, still with me. So please feel free to do that. What I'm going to attempt to draw for you at the beginning is what we're going to call regression by composition for a binary outcome. I'm going to draw some pictures. There won't be any numbers there or even letters. And then I'm going to reinterpret what I've drawn in a more abstract way so that it somehow has meaning beyond just a binary outcome. So that's the objective for the first pictures that I'm going to show you. So you will recognize, in the absence of axes and other helpful things that we often tell our students to include, but I have neglected to, this is one of the lab A plot style things that Rhian was including. So I want you to imagine, paint with your minds a sort of horizontal axis that somehow represents a kind of input probability of some event. So let's try to be a bit concrete. Let's say we're talking about a group of people who've been diagnosed with a particular form of cancer. We're interested in their 5-year mortality. So that's the event of interest. Maybe we've measured, just very crudely, some of them are younger at diagnosis and some of them are older. And also some of them, let's say we're talking about a trial, some of them have been given some fancy new treatment and some have not. So what I'm going to do is build up a binary regression model with those two covariate pieces of information. One is their age group, young or old, and one of them is whether they're treated or not. To do that, we're going to pass through, if you like, 4 layers, 4 components of our model. And the first is one of these risk ratio families of transformations. Now, in order to construct a model for anybody in the data set, we pick a starting point, and in a sense, the starting point is pretty arbitrary. In this case, we're going to pick. So we're going to pick a starting point. Actually, this is somewhat unusual for binary regression, but we're going to pick a starting point at the extreme where everybody gets the event. So that probability of death after 5 years equals 1. Now, that's just our starting point. That's not saying if that's part of the model. It's just a starting point. And then, so I'm going to be describing, first of all, the passage through this model of an individual who is young and untreated. Okay, so in the first component of our model here, we have, if you like, you can think of it like an intersect component. So everybody is going to get whatever transformation applies. No matter what group you're in, everybody will get this transformation. So our job in the first component is to estimate what is the transformation they get to the input of probability y equals 1 equals 1. What is the transformation that everybody gets in that first component? And so the model has estimated, in a way that we'll come back to, that the transformation that everybody gets is this sort of risk reducing. And of course, you would hope that it would be risk reducing if we've started at 1. Just in case I forget to come back to it later, one of the appealing features of starting at 1 is that immediately makes that intercept parameter, if you like, this risk-reducing model, it sort of makes that into precisely the risk in the reference category. So the estimate is precisely the risk, not an odds or something like that. It's a minor thing, but it's kind of cute. All right. So we've passed through with our young, untreated individual, first component of our flow, of our regression by composition. Okay, so we're now going to move into the second. This is where I require you all to rotate yourselves through 90 degrees because we sort of run out of dimensions already, right? So I want you to imagine now that the sort of vertical axis has become our new horizontal axis. Okay, so 0 is down here, 1 is up here, and the input risk is somewhere around about 0.4 for this person. Okay, and so you're now thinking that this is the input risk along here, and this is the new output risk. Does that make sense? Good, excellent. You're all doing the required mental gymnastics. And so what we're looking at now is one of these odds ratios or logistic regression type families of transformations, again, just like Rhian was showing us. Okay, so this is going to be the component of the model that's going to take care of the age comparisons. Now, because this is a young person, and I'm going to say, for arbitrary here, but that the young people are going to be our reference category for this model construction, necessarily, although there will be an estimated component to this, necessarily this individual is going to receive the identity transformation through this component of the model because they're in the reference group. So I think I do that. So all you're seeing here is that they're precisely hitting that identity line and emerging unscathed from the affair, as you say. So their probability hasn't changed at that point. So having passed through the intercept component that everybody gets and the age component that it may depend how old you are, you've passed through that. Okay, we're now going to have a third component. Here,
On pink fence.
I do apologize. I must have clicked something.
Canon.
Apologies to people watching online that didn't mean to do that. I do often give talks on missing data, but that was unintentionally. Okay, so we passed through intercept and age component. Now, what we're going to do now is have two further components, and this gives you a hint as to how we might be thinking about estimating models that have both a risk ratio and a survival ratio component, as Rhian was describing it, and a two-dimensional treatment comparison. So we're going to pass through the first of our treatment comparisons. And so now you're standing on your heads. So we have across here is the input risk, and across here is the output risk. Now, if you think about it upside down, this is one of those complementary log family of transformations, or the sort of survival ratio type models. Again, I've mentioned that this individual is an untreated individual. So again, necessarily, although there will be estimated components of the next two groups of transformations, necessarily this individual will be unaffected by them. So they're going to pass through unscathed through that one. And then finally, so having passed through a complementary log family of transformations, they're going to be passing through a log-link family of transformations, a relative risk style model, but again, necessarily passing through off the identity transformation. So really, this individual hasn't had a very exciting journey. They passed through precisely one transformation that did something, and then three others that, because of their covariates, didn't do anything. So that's the basic setup. So there's the four component, it is a regression by composition, by which we mean we're composing together families of transformations and allowing those to act on probabilities. Okay, the next slightly more interesting individual is going to be a young person who is treated. So again, everybody starts at the same notional starting point, and everybody passes through that initial model. This is still a young person. So again, through the age component of the model, they're going to be unchanged by that. Now at this point, we're into the treatment transformation components. As it happens, this is not necessary, but as it happens, the first of those treatment components has actually been estimated to have a null effect. So this is not structural, but it happens to have been estimated in this case. So the first of them, although not necessarily, this person, because they're treated, actually also hasn't had that affected by the first of those treatment transformations. However, it so happens that in this model, it looks more like a risk-lowering procedure is in play. And so in that final component of the model, this treated young person has an estimated risk reduction, so is affected by that risk-lowering risk ratio model, and their final treatment, for their final probability of 5-year mortality is lower than their sort of compatriot here who is untreated. Any questions before I go on to the older people?
Yeah.
Fine. So, same story. I don't know if you can see that. I hope you can. There's some purple dots there. But this is now a untreated older person. So older at diagnosis. Again, I'm repeating myself sort of deliberately here. Start at this arbitrary starting point. Everybody gets the same initial transformation. They are now an older person. So now there is the potential for an estimated age effect, if you like, to come into play, and indeed it does. So as it turns out, the estimated transformation that is going to be applied to an older person is a risk increasing transformation under this logistic regression component of the model. So their risk relative to a younger person is increased. So there it is, it's higher. Now, I've already told you that we're talking about an untreated individual in this case. So again, necessarily, they must pass through the next two groups of transformations unchanged. So in other words, they're going to hit that identity transformation in both cases. So this is where their final model probability has come out higher than the untreated young. Okay, so I'm hoping now that almost I don't even need to draw the final one, but we'll do it anyway. And so here we're now talking about a treated older individual. So here they go. They go through the first one, and as everybody does, they are older, so their probability is increased. They are treated, but as it happens, the treatment is the effect in the first component there is estimated to be null. So they go through unchanged there, but then Again, not necessarily, but we have happened to have estimated that there is a common treatment effect for old and young here. So they're going to be, in the final component, experience the same risk ratio transformation. So their final risk of mortality is reduced relative to their untreated comparators, and indeed even reduced relative to the younger treated. So we've started at 1, we've passed through 4 model components, and we've generated modeled probabilities for these 4 groups. Okay. So in a way, that is all a regression by composition is a way of combining together these families of transformations, stacking them and taking them sequentially in order to have flexible models that can deal with different covariates and different groups of covariates differently. And just to reiterate really what Rhian said, this idea was Anders's idea, and it seems a really beautiful and powerful and flexible idea. And really part of our contribution has just been to sort of take a step back, look at this picture, which he designed for binary data, and to say, well, if you kind of squint at it, these don't have to be just probabilities. And so what I'd now like to try and do is reimagine this picture where instead of along the various axes that I've drawn, you are thinking probabilities. I now want you to think probability distributions. So we have a straight line here. And of course, there's a kind of nice correspondence between a straight line and probability distributions on binary data. But really, in an abstract sense, you can have a straight line. Okay, it's not a straight line, it's a sort of affine space of probability distributions. And transformations can act on spaces or sets of probability distributions. And so there are, for the familiar models that we fit and know and love, there are analogs of the transformations that are acting here on probabilities that act on probability distributions. And I'll give you some examples of those in a little while. So if, when we reinterpret this, we're going to reinterpret the axes as affine spaces of probability distributions, and that's how and you can think of it just if you don't want to worry about the geometric structure of that, just think about a set of probability distributions. Then how are we going to reinterpret these families of transformations? So Rhian showed us several examples of the families. I want to call attention to certain features of them that make them particularly suitable for statistical modeling. So Rhian was describing that all of them, no matter what, have this sort of y equals x identity line. That seems like an important component. We want to allow the possibility in our models that different covariates or groups of covariates have no effect. That seems like a crucial point, so that the input distribution is unchanged by this collection of information. You'll also notice that each of the lines has the reflection of them in that identity line also present. And you'll remember from, probably GCSE maths that's the inverse function. So if you want to undo one of those, you have the reflection. So that is also an interesting feature. And as soon as you're saying the words identity and inverse for everything, you're thinking, oh, this is a group. And indeed it is. Now, I remember in my undergraduate days here, really quite being taken with the idea of groups. It's sort of, I think it was the first idea where maths could be beautiful precisely because it was simple. Like it would sort of strip away everything that we don't need and imagine this thing where there is only one operation that combines two elements in ways. So I remember being taken with the idea of groups. On the other hand, I remember not being very taken by the course on linear algebra and vector spaces. And I find that now unforgivable, but at the time, there we go, that was my 18, 19-year-old self. Because actually, I somehow feel that if somebody had told me, you know what, a vector space is just a really special continuous group, I think I might have been a little bit more excited by it. So what we're looking at here is not just any old group, but somehow, obviously, these aren't the only elements of the group. Anything in this whole sweep is an element of that group of transformations. So we have this continuous group, and that allows us, and it's actually a vector space. It allows us to talk about the idea of, well, what does it mean to do this transformation twice? Or even 1.5 times, or even minus pi times. All of those are possible questions to ask within a vector space. So that is an appealing idea in a statistical term, because we are thinking about, especially if you're thinking about things like dose-response relationships, you might want some sort of simplification that says, okay, well, if you double the dose, then you double the effect. That kind of idea. But we don't want to restrict those effects to integer values or so on. So we want that idea of continuous transformations. So I've invited you to reinterpret this picture. Now a picture that displays a series of transformations of probability distributions where they're going to pass through groups, vector spaces of transformations, and we're going to allow them to pass through several such groups on their way to their final destination. Each of the final destinations will also be a probability distribution, and I want you to think of that as the modeled conditional distribution given all of the covariate information. So does that make sense? So if we were thinking about, say, a linear regression, okay, so maybe some point in this notional abstract space, there's the standard normal. Okay, so the first thing we're going to do is pass through some group of transformations that scales that. Everybody is going to get a scaling of that changes the variance. So they pass through that, and they're going to come out at some other distribution that's normal still, but now it's got variance 100 or a variance square root of 2 or whatever. Doesn't matter. And then they're going to pass through a second component of the model that's going to take distributions and translate them. So it's going to take whatever input distribution it gets and add 100 to it or whatever. So it's going to crank through that X distribution, and that can depend on covariates, of course, and produce another normal distribution that now doesn't have a unit mean, it doesn't have unit variance or zero mean. So you can think about building up a number of models, familiar and more obscure. Okay. This is just a reminder for those of you who, like us, had forgotten all about group actions. This is so on the train here. I was thinking, can I find some fun example of a group action? And this is the one that popped up and appealed to me. So what we're experiencing here is a group in a vector space, in this case, acting on a set. And so the reason I've drawn this picture here is there's apparently a famous group called the lamplighter group. I'm looking to see if anybody's got, lamp bulbs going off in their head. Nobody. This was new to me as well. So I thought, well, coming to Oxford, home of Lewis, I got to talk about lampposts and lamplighters. Apparently, some people say that Oxford has the claim to the original Narnian lamppost. They note the proximity of this Mr. Tumnus-like figure to the lamppost here. But there's entire websites devoted to which is the original lamppost. So that would be controversial to go further than that. So this is the lamplighter group and how it acts. So apologies to those online. I was recalling to Rhian on the way here. I remember one of our Oxford lecturers trying to teach us about conjugation of group elements, and he did this sort of ballroom dance across the stage, and then he sort of turned back the other way. And I still don't understand conjugation, but I remember him very distinctly doing the ballroom dance. So here's my equivalent of that. I want you to imagine front of me, going off in both directions, a sequence of lampposts, some of which are lit, some of which are not. I am the lamplighter. And so the set on which the lamplighter group acts is knowing which of these lamps are lit and knowing my location. That's the sort of set on which it's going to act. And the lamplighter group is the possible instructions given to the lamplighter, like move 3 steps to the right and change whether if it's off, light it, and if it's on, de-light it. That's probably not the right word. And the idea here is that group takes as input some state of the system. In other words, where's the lamplighter and where the lights are, and it changes it, it transforms it. So you get a new lamplighter location and also a new set of whether the lamps are on or off. And with any of those, again, you can imagine that you can invert them. So in order to invert that, okay, I'm going to need to change that light back and then take 3 steps back to the left. So we have this group of instructions, transformations of the infinite set of lampposts. There's a slightly exotic example for you of groups acting on sets. But that's how I want you to think about what we're doing with regression in my compilation. For those of you who have a taste for the more abstract, my new favorite geometric object is an affine space. At least for this week, my tastes change quickly. I want to show you the sense in which these things are kind of straight line objects, a little bit like vector spaces. Straight line, I mean flat, I guess, objects. So this is what this is what the space looks like for binary data. So this is not a Lab plot now. I'm imagining trying to describe distributions of binary data. So in a weird way, you're carrying around 2 pieces of information: the probability that y equals 1 and the probability that y equals 0. Now, of course, for it to be a genuine probability distribution, you actually require that those 2 things sum to 1, and in fact that they are both between 0 and 1. So although it's sort of notionally a 2-dimensional piece of information, really it's only a 1-dimensional piece of information. Now, you can ask yourself, why am I worried about what goes on beyond that range? And Rhian has hinted at one of the reasons we might be worried about that is that actually, although the things down here and up here don't crop up, some of the models that we use, like the risk ratio model, and especially the sort of linear and probability model, can easily take us to distributions that are up here. So where we're assigning small negative, small negative probabilities to probability y equals 0, or indeed the opposite down here. So, and then especially for extreme covariate values. So this idea that we could apply transformations to distributions that are in here, valid probability distributions, but actually, unfortunately, end up outside that set, is a bug feature of some models that we use actively. And so getting an understanding of that is a useful thing. So really, I want you to imagine that, okay, so now if you threw in a 3rd dimension here, so we now have the probability y equals 2 is another thing, then you can probably imagine that this thing is going to become a triangle in 3-dimensional space. And then we have this plane of spaces beyond that where they still add up to 1, but some of them are negative. And so that's why I'm going to draw as a triangle the sort of simplex of probability distributions, but we're aware we may accidentally stray beyond that, and that's a feature. So that is an affine space, which is a little bit like a vector space. It would be really a vector space if it passed through the origin, but it doesn't, and it shouldn't. So it's sort of like a copy of the vector space that passes through the origin, but shifted a little bit. That's kind of what an affine space is, kind of where you've forgotten where the origin is. So this, in an abstract way, is going to be the axes that we are transforming. All right, so what we're going to be doing at each stage. This is sort of I'm going to now describe what goes on within each one of those components of the model. In each of them, we're going to be estimating a linear transformation. And it is a linear transformation that goes from some sort of covariate information. I'm going to describe it as a covariate contrast. So that's what I mean here is that I've learned something about this individual and how they are different from maybe a hypothetical reference individual. So that's what's going to be going into here. So the U is somehow the covariate contrast information that tells us something about this person. And then what we want to do is estimate a linear transformation of that into some effect that's going, like a transformation, if you like, or an effect size, is going to act on the group on the set of probability distributions. So we might, and these things can be for either the covariates or the effect sizes, if you like. So you might well, and in fact, this is almost exclusive what we do in practice. We almost always have our covariate contrast measured in additive real space, if you like. So, a standard example would be in a treatment contrast. The reference group gets 0 and the treatment group gets 1, and we sort of think about those as additive. But it's not necessary. You can imagine multiplicative contrasts where we're interested in this number is 10% bigger than this number, or 2 times as big. We certainly have multidimensional contrasts as well. This is also true of effect sizes. So any of these, either the input covariate information or the output effect size, any of those can be any vector space you like. One side note here, and it's not something we talk about, they sort of sit there in the background, but you can also imagine attaching units to some of these vector spaces, and that's quite attractive, the idea that in some cases an effect size of an increase of 3 millimeters of mercury or whatever is useful. And in some cases there won't be any units, especially if it's, say, a multiplicative effect size, so it's a doubling or a halving or so on. And I really like the way Terence Tao writes about this topic. It's sort of quite abstract, but also really concrete, that vector spaces anchor you to a world where you can't do weird things with units, like take logs of them, for example. So anything with a unit, you can't take a log of. That's kind of interesting, but you can double it. So this is, it sort of forces you to think about that. Now, it's not necessary, of course, to use this machinery, but anyway, worth thinking about. I've kind of said this, and I'm now going to say it again, but with the notation in front of you so that you can understand what I'm writing down further. So what I want to imagine is that, so we've now turned a covariate information input into, by way of that linear transformation beta, some member of a vector space. And that member is going to act to transform the set of probability distributions, which I'm going to write P. Now, you'll note that I haven't written the triangle here, because I am actually thinking about this affine space that includes not valid probability distributions, because I want to recognize that some of these transformations escape the simplex. So the way I'm going to write that is if I put a probability distribution dot V, I want you to interpret that as the action of the element of the vector space V on the probability distribution, or if I sort of leave that blank, that object is a transformation of that affine space of probability distributions to the same affine space. I'm going to say again what I said when we were looking at the pictures. These features of group action seem really appealing for regression modeling. So it's nice and essential, really, that we can say, okay, there's some identity element that's not going to do anything to any probability distribution. So this little p is just a generic probability distribution, not a probability, but a probability distribution. So there's no effect. We estimate it to be the identity. And also we have this idea of accumulation of effects. This is baked into the idea of a group action, that if you do the action of V, and then the action of v prime. Well, that's basically the same as within the vector space, adding v and v prime and doing that. So there's like a homogeneity assumption that's baked into the idea of a group action. So to us, it feels like a very natural structure to think about regression. So this doesn't mean multiplication, but it means the action of the identity element of the vector space on a probability distribution, just to emphasize that. Okay, finally, you get to see what a regression by composition looks like written down. So what we have here is a series of estimated linear transformations, beta, that take covariate information and turn it into a vector in a vector space. That vector, so yes, in other words, here's the covariate information. Beta turns it into an eta, a sort of linear predictor, if you like, that's going to act on. So this guy here, P0, is our fairly arbitrary starting point, our starting distribution. So that's the one that I picked to be 1 when it was binary data. And then it gets acted on by the first piece of information, that first group of transformations. And then it gets that thing, whatever the output of that is, gets acted on by the second set, and then so on through the third and however many chunks of the model there are. I'm going to stop at that point and see if there are questions or comments. Here's a word that I haven't used yet. These vector space actions, another word for them that is used, especially in the sort of dynamical modeling literature, is something called a flow. We liked that word for a couple of reasons. First of all, it's a single word rather than group action on the vector space, so it sort of condenses that nicely. And the second is it's a really nice word. So when we talk about flows, you can sort of, in your mind, extrapolate that to, expand that to group action set. The other reason it's nice is because actually quite often, and as we saw at Rhian's examples, you have the same group acting in different ways, like the group of positive real numbers under multiplication, acting in one case to reduce risks and the other to increase risks. So you can think about it, it's kind of a convenient way to talk about them, the risk ratio flow or the survival ratio flow and so on. So for binary data, as we've seen, there are groups of transformations that correspond to GLMs. We have also seen that if you start composing these together, you get things that you can't fit. Be described as generalized linear models. In fact, they're two-dimensional, and that's kind of interesting. Now, imagine you want to do some modeling of discrete data, like a count or something like that. So you can do all of the GLMs and so on and compose them together. You can also do things like compounding, where you imagine you've got the input distribution is being added to itself multiple times. That idea, or zero inflation, the idea that we're going to take the input distribution and more zeros. That's something that we often want to do in count models. You can do that fairly directly, and I think one of the appeals here is that we can do that without needing a kind of latent model for the zeros, as you sometimes need in zero inflation models. For continuous data, so basically anything that can be written as a transformation model can be written as flows. So that, by a transformation model, I mean kind of you're transforming the data, modeling the transformed data, and back transforming. The reason that we like that you can do that, but also that you can do that kind of directly, the subtle difference I want to emphasize is that we are transforming not the data, but the distribution. And so that allows you to retain the original scale of the data which you're working at all times. So that classic example would be one of the first laws of applied statistics is when in doubt, take logs, right? So you don't have to do that. What you really want to think about is multiplicative transformations of the distributions, but to retain the original scale. So in practice, it amounts to the same thing, but you're always working on the original scale. You can convolve distributions, or add them together, and one nice feature is, for example, it would be remiss in Oxford not to talk about survival analysis. And you can imagine situations in which you don't have scalar effects, but functional effects, time-dependent relative risk, or, for example, for the all-in survival model, you can have quite non-parametric components of risk difference or hazard differences. Okay, so this is just to say a lot of the standard things can be written in this way, and they can also be combined in interesting ways. And you can do things that are non-standard. The reason that we find the algebraic structure useful is because it allows you to express fairly concisely important statistical features of a model. And when I say this, I think what I really mean is important statistical features, important local features. So you can have components of the model that are or are not, we've used the word closed here. But what I mean here is that if you apply the elements of the group, the vector space, to valid probability distributions, do you stay within the valid probability distributions? That seems like an important thing to know about a local chunk of the model. It may not apply globally, but you can talk about it locally. Rhian mentioned to you already fixed points. I'm just sort of, again, rewriting them in the slightly more algebraic notation. So a fixed point is precisely one that says if I give you some input distribution and no matter what I do to it, I'm going to stay exactly where I was. That's a fixed point. A transitivity is a sort of group action word, but it really means if you start anywhere, almost anywhere, can you get to almost anywhere, almost any distribution? That seems like an appealing property to know about how flexible our model is. And similarly, and then this is a feature that is maybe less obvious until you start combining models in this sort of sequence. Well, does it matter which way around you put the chunks into the model? Seems like an important question to ask. And if it doesn't matter which way around, you might say that those two components, those two flows, commute with each other. Not all do. Some do, but not all. I don't think I'm going to spend too long talking about this, but it also allows you to start talking about collapsibility and especially beyond the binary setting. So really the idea here is that if you imagine some sort of random input distribution, by which I mean depending on covariates, and then we're going to act on it via some treatment information and then average it. Well, one sort of almost sense check, and this doesn't have to be satisfied, is, well, if I took the average input distribution and applied something across, within the range of the effect sizes that are possible for this treatment, does the left-hand side lie within the range of the right-hand side? And that's one definition of collapsibility. And as you may know, not all models satisfy that. So you can have things that sort of seem to defy logic and escape those bounds. And so, again, this is just a generalization of exactly what Rhian was showing already, that if you want a kind of strict version of that, then you need this transformation. So again, we're talking about just general probability distributions. You need that to be an affine function in order for it to get that sort of strict collapse. So that's an interesting feature. Okay, and then just finally, because we wanted to talk a little bit about fitting. Building things up this way actually allows for quite a modular fitting routine. So I've mentioned that all of the parameters are linear transformations. All of the parameters in a regression by composition. And each chunk really only has two partial derivatives that are relevant to it. basically the derivative of the flow with respect to its probability distribution input, and the derivative of the flow with respect to its vector space input. So, and if you've got those two, and those two things are not things that depend on data, they're a feature of the group of transformations. So if you have that, and you have a library of such things, you can imagine that by using the chain rule, you can build up quite easily, so I'd say easily, Rhian has done the coding. You can pipe these things together to get partial derivatives, derivatives with respect to the linear transformations beta, conceptually reasonably easily, shall we say. And the only additional component you need is at the end, when it spits out a probability distribution, you need to be able to convert it into a low likelihood, more likelihood, and have some notion of differentiating. All right. I want to very quickly show you an analysis just to show you how this works in practice. So take you back to 1977, where this data is from. We're talking about the value of fields in Minnesota that are used for growing alfalfa, and so that's the cost per acre is going to be the outcome. Some measurement of field quality is going to be one of our covariates, and then there's going to be a final aspect, which is whether the field requires liming. So basically, liming reduces soil acidity, but it's in a way it's a kind of additional cost that is going to be borne by anybody. If you're going to rent a field that requires liming, it's going to cost you a little bit to do this. All right, so I think this was as close as I could get to 1977 in my own mind. Anybody else remember Richard Scarry? No, not meaning anything. For alfalfa, that was what made me think of it. So here's the three flows that we're going to be using to construct our model. The first is basically you've taken input cumulative distribution function and you're going to shift it. So here's my distribution. This means shift by z. Okay, then we're talking about scaling, which is where you sort of, instead of shifting, you're scaling the cumulative distribution function. And the final one is the sort of equivalent one for powering. So you can think about these going up the operations, if you like, add in, multiplying, exponentiation. So what do those look like? Here's what they look like. If you imagine an input distribution, the red one, shifting or translating is going to have that kind of effect, where that amount is what's being estimated. The blue one is what happens when you scale the red one, and the purple is what happens when you power it. And these are all things that we can. So I'm going to show you 4 regressions, time permitting. This is one way of thinking about how you might write these. There's the cost per acre. Our starting distribution is going to be a log normal, standard log normal. We're going to have a sort of intercept chunk that is going to estimate a powered version of that. That's very, very similar. In fact, it's entirely analogous to the scaling of a continuous outcome. We now have a positive outcome, so powering is exactly the same role. And then scaling is analogous to translation in the additive world. So we're going to have in that final chunk of the model sort of intercept components, and then components for quality, soil quality measurements, and then whether liming is required. That's basically a standard log linear model. But you'll notice that I've written it not as a log linear model. The starting distribution is log normal, and then I've powered it and scaled it. So it's what you would usually write as log y equals alpha plus beta x, but we've started with a log normal. But you can do other things. So one interesting idea we thought was, well, what if liming basically has a fixed per acre cost? And it doesn't really make sense to think about scaling that. It would make more sense to say, well, okay, if there's a fixed per acre cost, and that's going to be basically translated literally into a translation effect of the distribution. So let's take that part out of this flow and put it into a separate component for liming. Or we could imagine, well, how much does this matter what distribution we start with? Maybe if we start with an exponential, we get a different handling of the tails, for example. Interesting, we can do that. Or, well, let's imagine that we actually can't make up our minds about whether we should have a sort of multiplicative effect of liming or an additive effect of liming. Well, let's do both. And this notion, I think, is quite interesting about regression by composition, that you can have multiple sort of the same covariate allow it to affect the distribution in more than one way. That's a curious feature. I'm glad the data tell us which one it is. I'm going to skip on to this one because I think it's a little easier. So, first one, the log linear model. So you can see here we go. Okay. So basically, if liming is required, so the two reds are the ones to compare the two liming distributions. Then the field prices are reduced. But you can see that it's not an additive shift, it's a sort of multiplicative shift. And you compare that over here where this is literally an additive shift. So there are different models of doing different things. I now want you to jump down into here and say, okay, well, this is the model that allowed either to happen. And interestingly, and sort of not what we expected, it actually matches closer to the multiplicative than to the additive effect. So we thought, okay, I'll show you, we don't know, well, I mean, this is not a surprise. We don't actually know very much about field pricing in Minnesota in 1977. But that was a surprise to us. A curious little feature is that for some small numbers of very low quality fields, if you like, there are some values where the distribution of costs might even be negative. And if you want to think about that in sort of economic terms, it's a bit like saying that field is so bad, and if I had to additionally lime it, you would have to pay me to rent it. It's almost that kind of thing. So, although it looks like a weird feature, actually, it's not necessarily a crazy idea. And just commenting on the shapes of distributions, these ones, interestingly, seem to skew to the left rather than to the right in the log normal case. So, and that's not necessary under what amounts to a generalized gamma model. Fine. Rather than go through this, I think I'd like to leave a little bit of time for discussion. These are just questions that we still are thinking about. So I'll stop at that point, and of course, thank you for your very patient attention through 2 hours of this. And yeah, very grateful for questions or comments.
In Spanish, I propose all those questions that are already online. So maybe we can start with Joe's.
I'm happy to read them. As an old friend online here. So Milan has asked, on the subject of group theory, where's closure? So I think what Milan is talking about is the idea that if you put two transformations together and the operation in these groups of vector spaces is composition, so composition of function, do you always get another function that is in that vector space? And by construction, in this case, yes, you do. So that's what makes it a group. So that's a really great question that Milan is asking there. And then, could the non-commutativity of different transformations be of relevance where the corresponding covariates affect people at different points in time? And the sequence may be different and make a real difference. So this is something we've thought a little bit about, but not enough. I think basically our instinct agrees with you, Milan, that where you have logically covariates acting earlier than others, so you might think about genetics or epigenetics acting before some later treatment effect. It does make logical sense to us to include the earlier components in sort of the earlier covariates in earlier components of the model. So I think that's a great shout. but it's also something that we had not thought enough about. And then a final question, and then I guess closure applies to the object of the action, so all the distribution. So I think maybe I'm not quite clear as to which closure Milan is talking about here. Certainly in terms of closure on the set of probability distributions, that's not a universal property, but closure in terms of combining transformations to give other transformations, that is a universal property. So I don't know if that answers your questions, Milan.
Yeah, I think I wasn't quite sure whether it was probabilities or transformations we're talking about.
Yes.
So.
Fair enough, and the answer is both. Very nice to hear you.
But is it also that, so if you take any element of the vector space, it will combine two elements of the set and give you another element that is in the set?
Yes, and that's true, yes.
And it's close.
And yeah, sorry, absolutely right.
So
yes.
if you with your P versus your triangle, P goes to P, but the simplex might not go to the simplex.
You got it. Thank you. That's a really good point, yes. So although the simplex of genuine probability distributions might not map to itself, P always maps to itself. Yeah. So that's really what it means for it to be a transformation. And indeed, any questions for Rhian's components and the idea about sort of first principles models as opposed to empirical models? I'm really interested to hear what you guys make of that idea. Is it new and interesting? Or indeed old and boring. You can tell us that as well. And then we will alone do something else. Actually, we won't, because this has been so much fun for us to work on. Even if it's old and boring, it's been new and exciting to us.
And what is it?
So I'll ask about really interesting. So how many transformations was it part? I mean, do you apply the same number of transformations all the time, or is it dependent on the nature of the problem determines how many transformations you can do? Why? And then here.
So just to make sure I understood the question you're sort of asking. So I've shown you examples that had 4 components, but then the ones that I showed you towards the end there, they had different numbers of components. And you're asking how do you decide that? I think what we're hoping, and I think we're too early to say whether this really works in practice, is that sort of in conversation with the people who understand the problem best, you can start speculating either from first principles or from subject matter knowledge to say this covariate or group of covariates we would expect to have a multiplicative effect or react in a particular way. So I think our idea is that it should be very subject dependent, and the hope is that it allows you to build models that are very subject matter relevant. So you're not forced. So for example, if you think about transforming data to do an analysis, what you're essentially saying is that all of the covariates have to act say multiplicatively, and if you think about it more in these local senses, that it allows you to say, well, okay, I believe as we imagined, although it turned out to be not the case, we might imagine that soil quality acts multiplicatively, and the cost of the lighting needed might act additively from subject matter reasoning. And that seems to us quite an appealing idea, that we can construct a model that matches what we think may be going on. And I think even more appealing if we can make some first principles arguments to say, this is why we believe this structure would be in operation for this local component of the model. So there's no limit in principle to these, to the number you can do. So to be determined really how they get used.
We've done the effect the error term, all those transformations.
Do you want to say a bit more what you mean by the error term?
The epsilon, no, I don't mean the authorities, no, in the models.
Okay.
The last term. And
The last term.
just the distribution mode.
Thank you. But both of you have. So this is something that I nearly said at the end. My very final comment was sort of going to allude to this. In a way, what we are trying to gently encourage is not thinking in terms of an error term, and there's sort of one obvious reason for it, which is that this error term is by construction additive, and there's no particular reason that errors, maybe do errors even exist, is a maybe more philosophical question. But certainly, why should we think about an additive discrepancy as being the correct way to think about deviations or variations? So I think I would echo what you said, that I think I would encourage you to think about the output of a regression model is a probability distribution. And so if you like, what do I want to replace this by? It's a notion of how surprising is this value in this distribution, not how distant is it from its arithmetic mean, but how surprising is it. So yes, it has strong implications for distribution of y, but I think we would like to gently nudge people towards not thinking about errors for both philosophical and practical reasons. But do you want to come back to me on that? Because maybe that's not quite what you were asking. Yeah.
So in a layman's term, we expect this probability to be around 0. So it's very likely scenarios versus that will not happen.
So I think, if I'm understanding what you're saying, in this standard decomposition, this is somehow a measure of the location of the distribution, and this is somehow a measure of dispersion. One of the nice features of regression by composition is that you can allow covariates to affect either location or dispersion, or indeed, kurtosis or whatever else you might care about. So the distribution, whatever the output conditional distribution is, still has kind of location and dispersion. So it still has a mean and a variance, unless it doesn't, of course, if you're talking about Cauchy. So they are, there's still a spread of values, and I think maybe that's kind of what you're driving at, and those are spread around wherever your distribution has been estimated to be located.
And maybe a consequence of that is that we find the pictures that you put up to summarize the results, sort of, that's a more, I mean, I know those are the estimates and not any notion of error around them, but almost that's how we imagine the results of a regression by composition to be communicated, isn't it? Albeit you would need some shading to show confidence intervals or something around those. It's not as easy to put these results into a table in a nice way compared with linear regression, probably because it's quite a simple model that acts only on the location. Then it naturally can be represented in a table more easily than maybe these results. But
yeah, I think so. Yes, I think we really like the idea of the output of regression modeling being conditional distributions and not just conditional means or conditional mean contrasts. That seems like an appealing flexibility. So, but yes, it does come with, as ever, whenever you go beyond one-dimensional things, it sort of comes with an associated complexity of communication. But I think showing distributions is a good way to do it.
What would the output look like for a binary outcome?
Yeah, great question. So in a sense, it depends a little bit on the components, but if we went back to this guy, so the first component was a risk ratio component. So there would be a single estimated risk ratio, and that would be a scalar. You'd be estimating the slope of that first line. The second one would have an odds ratio, a single odds ratio, which would be estimated, and that's the effect of old age relative to younger age. And then you'd have two further positive real numbers corresponding to the survival ratio treatment effect, the risk ratio treatment effect. So there's sort of four real numbers being, four positive reals being estimated: a risk ratio, an odds ratio, a survival ratio, and another risk ratio. So you can sort of imagine in table form that it's the different parameters have different meanings because the local components are different. But there's four numbers that specify that model. And of course, that's the most you could hope for in a four-group regression model. So this two-parameter treatment effect does sort of require there to be another covariate hanging around. Otherwise, we can't estimate two parameters from just the single and two-group comparison.
You could be silly question. Will this generalized pretty straightforward into probably distributions that have no parametric form, so non-parametric thing? Because essentially, if I'm understanding, you essentially transforming just the probability distribution. So I don't see any reason why you can't just slap it onto the parametric one.
So I think the answer is yes, but I don't want to say that too quickly. Let me just go back to maybe about these ones. So are you suggesting that somehow instead of having a specific, what part are you imagining becoming non-parametric?
Sorry, this has been a while since I've done the stats, so it's I'm sort of dragging it. I think the way I started thinking about this, I started thinking about how can you make this Bayesian, and I started thinking about the problem Bayesian, where the reason we do things like Monte Carlo is because you get to a point where you don't have a parametric form, you have to sort of estimate it, and I started thinking about, well, how would you implement that? I mean, maybe I'm trying to smush things together. They don't fundamentally go together. It's just
one way of thinking about what we're doing is that by putting these two things together, you are creating novel parametric families. So this is, as I've described it here, strongly parametric. But basically, if I started with, let's say, an exponential distribution and did different stuff to it, then I would get in this case, I got a generalized gamma distribution, but you could get other distributions by doing other things to it. So it's a way of building flexible parametric models. Now, one thing, I'd like to say a couple things to that because I think it's a great question. The one is that the more flexible you make these later components, the more. So if this next component is what I describe as transitive, which means you can get from any distribution to any other distribution. Now that would require this thing to be sort of infinite dimensional, but in principle, let's go with it. Then this becomes non-parametric or semi-parametric in the sense that I can have as my kind of reference distribution any distribution at all, and I can still have parametric treatment comparisons, for example. So something like the Cox model. One way of thinking about it is, let's start with an exponential distribution. Let's apply some infinite dimensional, and give it like the baseline hazard, infinite dimensional transformation to get to a reference distribution, and then a hazard ratio flow, which is a parametric component. So I think the answer is yes, that there's no reason that with sufficiently flexible flows, you can't get semi-parametric and non-parametric models. To your question about what does this look like in a Bayesian sense, there's absolutely no reason this can't be done in a Bayesian way because it gives you a likelihood. So you have the parameters are all linear transformations. So if you can put a prior on those, you have a likelihood that's what the model spits out. So you can definitely do a Bayesian.
I think I realized where my mistake was. Because I was thinking, no, basically the Bayesian I was familiar with, no, it is still parametric, it's just not of a known form, which is slightly different from not parametric. So I sort of got those flipped around.
Yes. And I think that's kind of what we're suggesting. This allows you to build parametric of not of a known form as well.
Tallies perfectly well.
Thank you. That's a really nice question.
Yes. The first is the getting is compiled.
Okay, great question. Is it implemented in R? alas, not yet. We have. It's one of these things that, in principle, we know how we'd like to make it work, but in practice, it's subtle. And what has been done so far is a proof of principle by which. So I was slightly. This slide was slightly misleading in that these things here, because if you remember what the kind of inputs are here, we're talking about vectors and probability distributions. These derivatives are not ordinary real derivatives. These are Frechet derivatives. So very much to my amazement, Rhian has actually managed to make this work with Frechet derivatives being coded in R for specific classes of models. So as a proof of principle, can be done in R. But it's not trivial. The idea, though, is that once these things are computed, it is a modular library that you can stack together, much as you would in the same way that with a GLM you get a sort of family of, Gaussian family with its inverse link and the derivatives of that. It's a similar kind of components, and you can stack them together. So we know what you'd like it to look like, but no, we had not. Do I have time to take up Milan's other question at the end, or aware that we are really pushing people's patience? Milan is following up on your question about if we abandon the y equals x beta plus epsilon decomposition, how do we express discrepancy between model and data? So I think that's precisely what the likelihood tells you. The way that's a description of the price of the data relative to the positive distribution. So I feel like a likelihood is a better guide of discrepancy than an additive residual. I think that's why I would like to encourage us away from additive residuals. So, you don't need E for the loose confidence interval between the goodness of fit test statistics what they went. Yes, so you don't need epsilon for those, is what Melinda's saying. Yeah, so it's a good question. I think the likelihood provides most of what you need to do statistics in whatever way you choose to do inference. So yeah, I don't think abandoning additive residuals means too much in terms of statistical practice.
Let's end Rhian Daniel again.